Well, thank you so much for the opportunity to be here. And yeah, Bill Hinkley played a huge role in this particular research. He was a huge advocate for research on treated wood, and I'm very grateful. Our whole team is very grateful for that enthusiasm that he gave to the topic. Okay, so as John mentioned, I'm with the University of Miami. And this is a joint project with 2 Florida universities, my home school plus the University of Florida. The co-PI on this project is Timothy Townsend. And I also like to acknowledge our students that are working on this project. Athena Jones, who's leading objective number 1 for the research, and she's works closely with Juniper Marini. And Nicole Roby, who's focusing on objective number 2. The motivation for this research, for those of you who are familiar with this study, this work, is familiar with the motivation, but for those of you who are not, a lot of this work began back in 1995 when there's a very beneficial recycling operation associated with the production of sugarcane, which is predominant in the central part of the state. Now, sugarcane has 2 streams associated with it. The liquid stream, which is used to produce the sugar, and then there's another stream, vegetative waste stream, the bagasse, or the byproduct of the sugarcane, which is then used as a fuel for cogeneration. The state of Florida has the largest cogeneration facility in the United States, and part of the recycling operation here was to use the ash from the cogeneration, from the burning of the bagasse, land apply that on the sugarcane fields, and then use that to produce more sugarcane. This was a beneficial process. We ended up with sugar, energy, and recycled waste. However, in the 1990s, they started accepting wood from other vegetative products, recycled wood from construction, demolition, recycling facilities. And at that time, they then started seeing hits for arsenic, excessive arsenic in the ash. As a result of that, they were no longer allowed to recycle that ash back onto the fields, and at the time it was a surprise. Nobody realized, well, what's in the recycled wood? What is causing this elevated level of arsenic in the ash? And it's the amount of ash at these facilities is huge. The amount of wood, I mean, the mountains of wood that are processed at these facilities is huge, and just to think that there could be enough contaminants in there is just was bizarre at that time. But we've traced it back to a wood preservative called CCA, or chromated copper arsenate. So our research was initiated almost 2 decades ago, and it was initiated as an ash disposal problem within the state of Florida. So one of our first tasks was back in 1996 to go to wood recycling facilities throughout the state of Florida. This work was led by the University of Florida group, taking samples at 12 different facilities in the state of Florida, large garbage cans full of mulch, which were then processed and analyzed, and then back calculated to determine how much CCA treated wood was in these mulch samples throughout the state of Florida. And lo and behold, we found a considerable amount of CCA treated wood in these mulch piles. Again, a lot of this was very new to us at the time, and it was unexpected. And at that time, the amount of CCA treated wood in these piles, on average for the state of Florida, was on the order of about 6%. So of 100 pounds, 6 pounds of that recycled mulch had CCA in it. In addition to the disposal issues that were of concern at the time, in addition to all of that going on, there was also a lot of initiatives at the federal level due to concerns raised about in-service use of the wood. Before 2004, they would use this wood for making picnic tables, for children's play sets, and there was research that was initiated not only by our group, but groups throughout the world that showed when children play on these play sets, you measure the dust on their hands, swab their hands, and you can detect the arsenic on their hands. And so because of this detection, this public relations issue that was raised with CCA treated wood, not necessarily because of the disposal issue, more because of the in-service use in residential applications, the industry, because of the public perception issue, voluntarily withdrew CCA treated wood from residential applications effective 2004. So there's been a lot of changes since our study back in 1996, where we now experience a phase out of CCA treated wood. What are the markets for CCA treated wood? In Florida, the most common markets are for use as boiler fuel, for producing energy, and also for mulch and producing mulches, decorative mulches. A lot of our work in the past has also focused on separating and sorting the CCA treated wood from the untreated wood. Recycling of C&D wood is a good thing. We want to promote that, but we want to get the arsenic out. And so we've developed various techniques for doing that. Various methods include visual identification. So if the wood has very large dimensions, such as a utility pole that is green in color, we know that's CCA treated. In addition to the visual identification based on the shape of the wood, any outdoor wood, such as fences, if you can still see the pickets on the fence, that's CCA treated, if it was produced prior to 2004. We also develop new technologies based on X-ray fluorescence. You put it on the wood, and within a matter of seconds, it'll tell you what metals are in that. Those XRF devices, however, are expensive, and so we've also looked into using stains, more affordable, low-cost stains for identifying metals in the wood as well. Before I get into the specifics of our research, I want to give a little bit of background on the types of treated wood, a little bit more information on treated wood itself. For the most part, throughout history that we have, especially since the 1980s, the distribution of wood treatment preservatives in the market can be separated as follows, where 60% of it is waterborne. So waterborne preservatives are those preservatives that soak into the wood and they don't have a smell to them. When the wood doesn't smell, you can paint the wood. It's much more user-friendly for residential applications, and that represents about 60% of the market since 1980. Creosote represents a third of the market. That's the dark, smoky smelling, oily type wood. And then there are other oil-borne preservatives such as pentachlorophenol that are used almost exclusively for industrial applications. The type of wood that is most problematic with recycling is when you have lumber and timbers, fence posts that have been already separated out. And so you can no longer tell if it came from a fence. And that gets mixed up with untreated wood. And it's those smaller dimensions, the ones that are most commonly used with the waterborne preservatives that are the most problematic in the disposal sector to identify visually treated from untreated. So before 2004, the vast majority of the waterborne preservatives were CCA treated, chromated copper arsenate. But because of the 2004 phase out, about half of the waterborne preservatives converted over to the copper-based alternatives. So we still have CCA treated wood that is manufactured. It's not manufactured for residential applications, but it is manufactured for marine applications, for farm applications, and for industrial applications and utility poles. But for all the residential uses, we have these copper-based alternatives that have copper but don't have the arsenic. This is what CCA treated wood looks like. So I made a mention about the green color associated with CCA, and the color changes depending on the amount of chemical that's been added to the wood. You have a very light green color for the low retention levels versus a dark green for the higher retention, which are used for more extreme applications. And this is in comparison to the untreated southern yellow pine, which is the most common type of wood that's used to treat for treatment, which has a yellow color. So looking at the metal concentrations in CCA, as you can see at the low retention level, the amounts of the metals, arsenic, chromium, and copper are on the order of thousands of milligrams per kilogram. At the highest retention levels, we have tens of thousands of milligrams per kilogram in the wood itself. And if we compare that to the soil cleanup target levels, there's a huge disparity in the levels that are typically allowable in soil applications versus what we see in the treated wood. There's orders of magnitude differences, especially for the arsenic. And the low SCTL for the arsenic reflects the higher toxicity of arsenic to humans relative to copper and chromium. This low tolerance for arsenic results in it makes it really difficult to recycle wood, especially when you have 6% coming into the wood waste stream of the total waste stream, of the total wood waste stream. If we want to meet the residential regulatory limits for soil cleanup target levels, you could only have 0.4% CCA treated wood in that pile of wood, less than half a pound per 100 pounds of wood that are recycled. So there's very strict criteria if we're going to recycle that wood and maintain the wood at levels below the SCTLs. As far as the alternatives to CCA, the alternatives that came into being after the 2004 phase out, again, as I mentioned before, had more copper. They're copper-based alternatives. Examples are shown here. They also have the green color because the green color in CCA is from the copper. It's not from the arsenic. So CCA is green because of the copper, but then also the alternatives have the green color associated with them. Common alternatives, copper-based alternatives, are alkaline copper quat, copper boron azole. There's been changes in the copper-based alternatives to micronized formulations which limit the leaching of the copper. And again, this is in contrast to the more yellow color associated with untreated and borate treated wood. Now, comparing the treated wood, the metals concentrations associated with these different alternatives to CCA, as you can see, the CCA has high levels of arsenic, has high levels of chromium, and it's the copper where they're more comparable, and the alternatives have more copper, about twice as much copper as the CCA. So there's a balance between the copper and the arsenic. Copper being less toxic to humans makes that balance a little bit easier to deal with when looking at regulatory criteria. So that brings us to our research motivation. And our research motivation, essentially, why are we revisiting this? We looked at it 20 years ago, we looked at it 10 years ago, why are we revisiting this? Well, in 2016, the US EPA issued some new criteria called non-hazardous secondary materials, which, as long as you have construction demolition waste that is sorted based on best management practices, you have a wood waste that results is considered a non-waste. And as a result, there are more lax, what I consider to be more lax air emission standards for the wood burning facilities. And so a lot of questions were raised at that time as to, well, we have BMPs in Florida. Are they working? They were implemented back in 2006. Are they working? How good are our BMPs? How good is our wood waste stream? What can we expect at these wood fuel facilities, assuming that they do sort based on BMPs? So our last set of BMPs, as mentioned, were published in 2006. This was a collaboration with the Hinkley. It was called the Florida Center at that time. It's now called the Hinkley Center for Solid and Hazardous Waste Management, and the University of Florida and University of Miami. And so our focus in this study was to update these BMPs as well. So our research objectives to address issues to answer the questions is, are the BMPs good enough? Are they working? We separated into three objectives. Number one being we want to update our disposal forecast. We had developed a disposal forecast to determine how much more arsenic was going to be coming into the waste stream, how much, was it going to decline, was it going to go up? We also wanted to double check our forecast based on what we can measure out in the field. We wanted to go back out to these wood recycling facilities and measure the amount of CCA in the wood piles. And then as a result, we wanted to update our guidance documents. So again, that brings us to objective number one, which is updating our disposal forecast. And this is our original forecast, or the latest version of the forecast back in 2004. And what the forecast shows us is that in terms of, we're looking at metric tons of arsenic from CCA. And back then we were in the 1990s, and what it showed us is that in the production side of CCA, the amount of wood that was being produced kept going up and up and up. It was exponential at that point in time. I mean, the amount of CCA was just growing incredibly. And as a result, our disposal would also be increasing. Now, in our forecast, we also take into account the fact that CCA leaches a little bit of chemical over time, very small quantities over time. So the longer the wood is in service, the more chemical that you lose. And so our model took into account the leaching of the CCA, but regardless of taking into account that leaching that occurs during its in-service use, there's still some in the disposal sector. And back in 1995, we were on the upward rising limb of this disposal forecast. And we were interested now to see, well, now we're on the falling limb, almost at the same level as before. The amount is at the order of 500 metric tons being disposed per year, but here we were on the upswing and now we're on the downswing. We wanted to get a sense of whether or not our BMPs, how good was our sorting at the wood recycling facilities. So our updated forecast, this is our original forecast where we looked at various commodities, the timber, fence posts, poles, piles. We updated it, we added some additional commodities, the cross ties, switch ties, which we found in some of the more historical records that were treated using waterborne preservatives. Our model takes into account that there's a certain amount that's wasted right off the top, about 2.5% when the wood is first used, and then it goes into disposal forecast, and we have different service lives for different products and commodities based on literature reviews, such as, for example, the lumber and timbers are on the order of 10 years, or if they're used for residential applications, or 25 years if they're used for highway guardrail posts, for example. So taking all of these service lives into consideration, we then forecast the disposal. Our model includes 8 commodities, 21 preservatives. As I mentioned, CCA was predominant during the 1980s, but before the 1980s, there were other chemicals. And since the 1980s, the chemicals have also changed. And so overall, there's a total of about 21 waterborne preservatives that we keep track of. And this model, the old model only considered arsenic, but what now we are also considering arsenic, boron, chromium, copper, and zinc. Oops, sorry about that. And this is our model, and sorry, John, this is an equation, but I'll go quickly through it. But what the model is based on is that the amount of wood in service is the sum of what's been produced over time minus the amount that's been disposed. Our updates were going back to 1909, the early 1900s, which is when the records from the wood treatment industry are available. We're also, in addition to taking into account CCA, we're also taking into account the 21 preservatives that have alternative waterborne preservatives. And we're also taking into account the service lives. So this is our production statistics. These are back in the 1900s. The CCA, or the waterborne preservatives that had been produced over time. Back in the old days, it was zinc chloride. Then they experimented with a lot of different other preservatives. Again, we're at less than 100 million cubic feet. But then we go into the 1980s, and you see the exponential increase once CCA treated wood, or CCA is discovered. And also at this point in time was a time when wooden fences became more popular, wooden decks outdoors became more popular with homes, and so you see the incredible increase in the CCA treated wood production. And then we had the phase out in 2004, which then opened the door for all of these alternatives to CCA. There was a big drop here. This is when the housing boom declined in about 2010, 2011, and now it's picking up again. So in our previous slide, we were at about 800 million cubic feet. So in our production statistics, again, we're about 800 at our peak. And then our disposal forecast, again, shows that we are in this period where the total amount of treated wood disposed is at a lag and smoothed out given our production statistics. And again, we do anticipate the total amount of treated wood disposed to increase over time. This is the statistics for arsenic, and again, this is metric tons of arsenic. The amount of metric tons used in the production is illustrated here. We also take into account the amount leached and then the amount disposed. We're right now at about, in this part of the graph, at about 2016. So yes, we're definitely on the downstream side of the arsenic disposal found in the disposal stream, which is a good thing. And then, but for copper, again, we are finding that the amount of copper disposed is pretty much going to go up and then maybe remain pretty much steady over time. So we have certain numbers for the prediction of arsenic and copper in our treated wood. Our next objective was, can we ground truth our study based on actual measurements in the field at treated wood facilities? And then the way we're calculating that is the total mass of CCA, the total amount of CCA is a product of the amount of C&D material, the fraction of wood in the C&D material, and the fraction of CCA within wood. And of these 3 parameters, these 2 are pretty well known and well documented. We are focusing on characterizing the fraction of CCA in C&D wood. As far as the typical composition of C&D waste, assuming that the circles represents the entire composition, 6% by weight is wood. By volume, it would be larger. But these numbers are pretty well documented, not only through the CDRA, but also through the FDEP. So that brings us to our focus on looking at the fraction of CCA in recycled wood. And so we go out to wood recycling facilities and we go randomly collect samples from a pile, and then we have 20 samples per pile, and we analyze them using X-ray fluorescence, which gives us readings right in the field. And we also take these samples and put them in a garbage can and take them back to the laboratory and then have them analyzed using the more rigorous laboratory equipment. So examples of the samples are illustrated here, where we have, we take these samples of mulch, we ash it down to get a smaller volumes that we can then process through our laboratory and analytical procedure, which is then analyzed by ICP. The results of this work, again, we're focusing on the fraction of CCA within the wood waste stream. And these are different facilities that have been visited. And if we take the average for CCA, for all of these facilities, it's on average 2%. So 2% is low, especially given that our previous estimate was 6%, telling us that there seems to be about a threefold decrease in the CCA treated wood within the disposal sector. If we add up these two together, which gives us 4%, it's still lower than the 6%. So I do believe at the time, back in 1996, it took us a while to get this published, but this is data corresponds to 1996. What it tells us is that back then we didn't have best management practice. There wasn't as much awareness as there is now about CCA treated wood. And so even if we add these two together, I still do believe that our BMPs are doing something to help us in decreasing the overall amount of CCA that's being recycled. Just to illustrate the different preservatives or the different metals in the wood waste, not only was arsenic measured, as illustrated here, but the copper was also measured. And for each of the samples, this is at source H. H is this one here. At source H, based on the chromium, we can back calculate what fraction of the sample was coming from CCA, and then based on the copper and the difference from the CCA, we can then figure out how much comes from the copper-based alternative wood preservatives. So that brings us to research objective number 3, which is to update our BMPs. And within our updated BMP, again, the original BMPs were published in 2006, and were published in 2006, and this updated version of the BMP now has an updated disposal forecast in it. It also acknowledges the alternative copper-based preservatives. The original BMP did not have that because we didn't have that much information. It's been over a decade now, so we know a lot more about the copper-based alternatives. And then it also includes new technologies for separating and sorting treated wood from the wood waste stream. These new alternatives include new chemical stains that have been developed since 2006, more information on the use of handheld XRFs, and also includes new research on online sorting systems for X-ray fluorescence. This is an example of the new guidance document illustrated here. Again, it's a 2017 document. We are going to release it very soon. I have copies of it if anyone's interested in taking a look at a draft. So to wrap up, what we can say is that the amounts of arsenic in the disposal stream are decreasing, which is a good thing given the toxicity of arsenic. We do recognize, however, that this increase in this decrease in arsenic is counterbalanced by an increase in copper. But again, copper is less toxic than arsenic, so this trade-off is a good thing. And we also recognize that the BMPs do appear to be helping, in addition to this changeover from arsenic to copper, there seems to be some positive impact from the use of BMPs at wood recycling facilities. And also to close up, I just wanted to emphasize that the updated BMPs will be published soon. So at this point, this is a picture from about a decade ago, and this is me a long time ago, and this is Tim, and this is us today. And I'd like to acknowledge the Hinkley Center for Solid and Hazardous Waste Management for making this work that has spanned a long period of time possible. And I'd like to ask if there are any questions. Thank you.
So as the there a potential for adverse effect on our environment for the increase in copper?
That's a great question. We're very sensitive, humans are very sensitive to arsenic. We're less sensitive to copper. But the aquatic environment, the aquatic organisms, copper it's very toxic to the aquatic organisms. So the copper-based alternatives would be more toxic to the aquatic animals. Now, CCA still continues for marine applications. So perhaps in that particular environment, it may be better to maintain the CCA, although there's still a lot of human contact with CCA in that environment. So yes, there's more, from a human health point of view, the copper is less toxic to us, but from an aquatic organism point of view, it's more toxic.
So that would be a good research topic for next year, right?
Oh, that would be wonderful. Yes, we would be very interested in studying copper in aquatic environments, copper-treated wood.
What do you think of the things that replace CCA? Do they perform as well as CCA?
And that's another really good question. I had to replace the roof of my house, and I had to make the decision. And I had a hard time finding alternatives that would work as good as CCA. I had to pick from cedar wood or copper-based alternatives, and knowing that they don't potentially perform, from a structural point of view, they don't perform as well. So yes, from a structural point of view, CCA, the interesting thing about CCA is that there's chromium in it, and that chromium fixes the copper and the arsenic to the wood. And it's a potent termite, it keeps termites away very, very well. And the arsenic is really good at keeping the termites away. That's why I had to replace my roof, it's the termites.
So you use CCA plywood?
No, we did not. We did not use CCA. We ended up going with the cedar wood. Yeah.
Thank you.
Okay, thank you.